So we are starting lecture number 14 of EE 543. So let's remember last time. So we have discussed diagonalization of covariance matrices. Okay. So as I have said many times before, covariance and autocorrelation, there are two types of matrices. One of them is assuming zero mean random vectors, and the other one is assuming, in a way, non-zero mean quantities. One more time. Rx is autocorrelation matrix. This is X solution. Cx is covariance matrix. And this one is X minus X bar, or the mean value of X vector, X minus expected value of this. So my previous sentence is this. As you see, I have the outer product of two vectors over here and I calculate the expectation. This is called autocorrelation. And this is almost like the same, but as you see, the only difference is the following. Now I again have the output product of two vectors, but this vector is mean subtracted version of this vector. So I'm subtracting the mean vector, as you see over here. So you may say that this is a zero mean quantity, this is a zero mean quantity, so this is the outer product of zero mean vectors. So this is called covariance matrix. Of course, if the original vector x has zero mean vector, okay, then they are coinciding, so they are the same. This was my previous sentence about the difference between covariance matrices and autocorrelation matrices. So what is our goal? Last time again. So given, let's say RA, or you may say CA, whatever, then our goal is find a transformation T such that T times, let's say, let me write Rx, okay, given Rx, which is equal to X permission. So let me say y over here, such that y is equal to t times x, okay, and ry, according to this, is diagonal, is a diagonal matrix. Okay. So this is called diagonalization of autocorrelation or covariance matrix. So what is this? This is the T matrix, this is the transformation, you may say, of this X vector to another vector. So this is also a random vector, but the property of this random vector is now its autocorrelation matrix is a diagonal matrix. So last time we have seen the following: diagonalization by eigendecomposition. This is if Rx has eigenvectors listed in the E matrix. I'm not giving further details. Then what we have seen is T is equal to E Hermitian. So this is the transformation. T is equal to E Hermitian, meaning that I calculate the inner product of X vector over here, inner product of X vector with every eigenvector of Rx, and this becomes the representation of Y, as you see. Okay. So an arbitrary vector can be represented like this, because this is an orthogonal set. spanning the n-dimensional space also I can do this. And last time we have shown that this diagonalizes the covariance matrix. So there is a picture about that. For example, if I have a level curve, so this is, let's say, two-dimensional, x1, x2. So if I have x solution, Rx, something like this. If I apply this t, y is equal to t times x, then, so I have a two-dimensional y vector, okay, whose entries are y1, y2. But what is the property of this vector? Now it is aligned with the axis. Okay, this ellipse is aligned with the axis. Okay, this is called the diagonalization from this quadratic product. Now I have y permission, y, y. So this is the level curves for that. So what we see is the alignment. Okay. Number 2. So this was diagonalization by unitary transformation followed by, let's say, scaling operation. Let's do not use this one. So what is the purpose of this? Now I have a T matrix in this case defined. Last time again we have covered this. So T matrix is the follows, as follows. Okay. So this is the T matrix of, as you see this case number 1. So now you can assume that now I'm applying this T mapping to this x vector. So if I apply an x over here, then E permutation times x is this kind of mapping, because this is this. Now for this one, there's one more scaling. So let me call this then z. Z is equal to, let's say, t times x. Okay? Then this is equal to minus 1/2 E permutation x. So let me call this y. So this is then this part. Now y is mapped to z this time. Okay? So this is the part, unitary transformation followed by scaling. This is a unitary transformation or orthogonal transformation. Okay. So this is Ry aligned with this. Now I'm doing one more operation. Now I'm entries of the z vector, z1, z2. Now they are circles, concentric circles. Okay. So this is the mapping z is equal to minus 1/2 times x, so times y. Okay. Because this is y, I have this, I get that. So as you see right now I have concentric circles. Because of this scaling, I'm scaling x and y axis. I get this one. Again a diagonal matrix. So that was the third one. So this is by LU decomposition. By LU decomposition. Okay. So what's going on? Now this is also something similar, but now I have Rx matrix. Rx matrix is, last time we have discussed this, it can be expressed as LU, a diagonal matrix, and let me say dx, diagonal matrix of x, okay, and LU permutation. Okay. LU is unit lower triangular matrix. Okay. Now if I have such a case, this is by LU decomposition, then T matrix, if I select the T matrix as LU inverse, okay, then this is also diagonalizing another diagonalization matrix. Okay. Well, in the literature, this is also called, well, write this as, for example, Q times Q Hermitian. You can, from here, by defining Q, a Q matrix, LU times dx, let's say 1 over 2. You can write it like that if you wish. This is called, maybe in the literature you are familiar with, as Cholesky decomposition. Okay? In MATLAB, there is a command, chol, okay? As far as I remember, if you write something like this, you get Cholesky decomposition, this Q matrix essentially, of this A matrix, okay? Of course, as you can see, this has to satisfy some symmetry properties. Now, if you have that, you are done, because from this Q, you can have this, and so on, okay? Well, what else? In MATLAB, you can get these eigenvectors by I command. Okay, that's also easy to achieve. What else? That is it actually. Now, today we are starting another topic, number 4. So I'm erasing this. This is also quite important in many applications, and it's not very trivial. So at the end, we will have a third command. So this is I command to get you the eigenvectors. This is a Cholesky command. Okay. Now there will be a third command for diagonalization, but this is a little bit of a different problem. So the joint diagonalization of two covariance matrices. So what's going on? Now I don't have a single covariance matrix, but I have two covariance matrices. Okay. Now let me sketch the situation. Now let's say that I have something like this. Let's say this is A, covariance matrix number 1, and I have another one over here. Okay. Let me also make this, let me also make this not aligned with the axis, okay, in a strange shape. Maybe something like this. So this is A, and this one is B. Okay. I hope it's clear what my intention is. I'm talking about the level curves associated with these covariance matrices. Okay. So this may be autocorrelation matrix, because as you see, this one is shifted from the origin. Okay. I have something like that. So these are the level curves. Very similar to this, as you see. Okay. Now I have A vector and the B vector. So what I want to achieve is, I want to align, I want to find a transformation such that it is aligning the axis of these two, let's say, ellipses with the axis of my representation. Okay? That is it. That is my goal. So how can I do that? But I want to align both of them at the same time. Well, I'll be doing this in 2 steps. So let me write goal. Given, let's say, RA and RB, okay, find T such that after transformation, i.e. T, RA, T Hermitian operation, and T, RB, T Hermitian operation, we have a diagonal covariance or autocorrelation matrix. Okay. So this is a mapping for the autocorrelation matrix, as you see. So vector is mapped like this. When the vector is mapped, random vector is mapped like this, it is covariance matrix is mapped according to this. But I want both of them. We have diagonal matrices. Not a single one. I want both of them to be diagonal. Okay. So how can I achieve this? Now I will do this in 2 steps. So step number 1. Okay. Now I will define a T1 matrix as follows. This is step number 1 transformation. So this is A matrix. I want to do something like this. Minus 1/2 EA revolution. So what is this? Now I'm assuming that RA is represented like this. This is this level curves. EA, a diagonal matrix, eigenvalues matrix, and E Hermitian. Okay. So this is the eigendecomposition of RA matrix. Now if I apply T1, what happens? Well, if this is A, then at the end of the first step we get concentric circles if I apply this, because this is not about diagonalization by unitary transform followed by scaling. Well, this is the same as the second one. So this is the step number 1. So let me write. So at the end of step 1, we have, let me draw a picture for this. Now A, after transformation, this is concentric circles. So this is A after step 1. Okay. But what happens B? If I apply the same transformation to this B, now it will be something different. Okay. So this is B after step 1. Because as I have said, I am looking for a single T. This T should be applying on the A vector and the B vector, and at the end, both of them should be aligned with this axis. Okay. So if I apply this T1 to A vector, I get this. If I apply the same T1 to this B vectors, then I get transformed version of this. I have no control over this because I have only converted this one to circles, but I have no idea what has happened to this one. Okay. Now let's erase this part. So this is the end of step number 1. So half of the work is done. So the remaining part is diagonalization of, B after step number 1. So how can I diagonalize that one? Step 2. This is rather easy. So let me define RB, let me say after step 1. So this is T1 RB T1 Hermitian. So this is this matrix. If B vector is mapped with T1, okay, then this is the autocorrelation matrix after step number 1 with level curves like that. So how about this? Now diagonalize RB step 1 with, what's your guess? Eigenvectors of RB step 1. Okay. So in other words, now this is, so this after step number 1. And if I do this, forget about this one. If I find the eigenvectors of RB step 1 and use it as my basis, then this will be also aligned like this. Okay. So this is after step 2. Am I right? Because this is again an autocorrelation matrix. If I choose the eigenvectors like that, then I can also align with this one. Don't worry whether this is, has zero mean or not, because this is, as you see, related with the mean of this vector. don't worry about this, center, let's say. Okay. So it will be aligned according to that. Now the question is, if I align B, what happens to this one? Am I losing this alignment property that I had achieved after step number 1? Well, question. So if we align, let's say, if we diagonalize, let's say, RB step 1, okay, is the alignment property of RA, this part. Step 1, after step 1, concentric circles. Concentric circles is lost or not. Okay. Well, so what should I sketch for this one? Is it aligned or not aligned and so on? So what's your answer? Answer is, well, let me see. So this is RB, step 1. Let's say that it has eigenvectors, EB, let's say step 1. Okay. Lambda K, EB, step 1. Okay. So my mapping is, my T2 mapping is at the second step. So I am E1, E2, let's say EB1, B2, EBN, step 1, step 1, step 1, and I have the permission of these. Permission. Let me write permission so it will be more visible. Permission of this, permission of this, permission of this. So let me of course write this as EB, step 1, permission. Okay? So this is as we have discussed a few minutes ago on the diagonalization of covariance matrices by eigenvectors. So what is the property of this? Again, these are, because this is a permission symmetric matrix, as before, these are orthogonal. These are orthonormal, even orthonormal vectors, meaning that this already RA after step 1 is already identity, because A after step number 1 is already identity concentric circles. Then T2 RA, T2 permission. So I'm applying T2 mapping over here. So if I call this, what should I call this vector? So previously I have, let me write over here. This is my T1 mapping. This is my T2 mapping, and this is RA after step number 2. Okay. But this is also identity. The reason is this is identity. T2 times T2 permission is, these are orthonormal vectors. So I get identity for this one. So the conclusion is nothing happens to this one. Nothing happens. So I see concentric circles over here. These are ellipses, concentric ellipses, but what I see is, let me draw this a little better. What I see is alignment, as you see. Axis of the major and the minor axis of the ellipses align with the axis of my representation. Okay? That is it. That is the end. So what is my final answer? So RA after step 2 remains decorrelated, aligned level curves are aligned with axis. Okay, major and minor axis matches. So one last thing. So final mapping is, what's my final mapping? You know, T final. So first I apply T1, then I apply T2. This is my final mapping. So what's my T1? T1 is this. Eigendecomposition of A times this. Okay. So what is T2? T2 is this. Maybe I should write this over here in a different color. So this is EB, step number 1, permission. Okay, something like that. So, original vector, first step mapping, second step mapping, final picture. Okay. Now here's one other thing. Now we have understood the topic. Actually we got the final result, but can I calculate this final mapping, you know, in a single strike without so much effort? So I want to combine these two steps together. How can I combine those steps together? So let me do as follows. Okay. So let me look at this. So this is RB. So I'm focusing on step number 2 right now. RB, EB, after step 1, is equal to, there is some lambda k, EB, step 1. Okay, I have something like that. Now, what is RB? RB is this thing. T1. So this is original RB before step number 1, given RB. This is T1 permission, as you see over here. Now, if I insert this for this one, would you agree that I get something like this? RB, then T1 permission, EB step number 1 is equal to lambda k T1 inverse EB step number 1. Okay. So what did I do? I have placed this one over here. Then I have moved this T1 on the leftmost side by multiplying by its inverse. And that inverse is appearing over here. So these two is this two, and done. That is it. So what else? Let me write just a second. Let me process this a little bit further. T1. Oh, let me write now what is over here? You know, T1. T1 is this. So I'm trying to express everything in terms of EA and A or B matrix, the given matrices, you may say. So what's the inverse of this matrix? Inverse of this is EA, because inverse of this is permission. This is inverse of this is 1/2 plus 1/2. So this is this part. Now I will introduce some matrices over here. 1/2 EB, step 1, and I will erase some part of this. Okay. So what did I do? Now this is this part. Okay, we have explained that. How about this one? So this product is identity. Then these two matrices, E matrices multiplied is identity because they are also orthonormal. How about this? This is also identity. So I have included an identity matrix over here. Okay. So if I do this, what do you see about this one? This part. And this part. So this is the lambda k. Well, this is the eigendecomposition of RA, given matrix at the beginning, the first matrix that we were given at the beginning of the problem, RA. So this is equal to this. How about this one? Well, this is T1. Let me see, T1 Hermitian. Let's see. T1 is over here. T1 Hermitian is this one. Okay, the second one. Okay. And we have the final vector over here. EB, step 1. Okay. So this is looking more complicated, but as you see, at the beginning of the problem, I had RB and RA and nothing else. Okay. So I'm trying to combine these two steps as you see together. So if I write, for example, this as my, F vector, F, okay, a vector F, then this is also F, am I right? Then what do I have? I have RB times F is equal to lambda k RA times F. Okay. If I call this an F vector, at the end, I get something like this. So you may wonder, what is the purpose of defining F, but at the end, F will turn out to be our final mapping. Okay. But let me say something. This is called generalized eigenvector. Generalized eigenvector of RA and RB. Okay. Why do I call it generalized eigenvector? If this matrix is absent, or its identity, this is the classical eigenvector relation. F becomes the eigenvector of RB. If RA is present, then this becomes generalized eigenvector problem. And of course, if you move this, if you can take the inverse of this matrix and move it over here, by multiplying from left by the inverse of this matrix, this becomes, if I move this by multiplying the inverse of this matrix, or A inverse both sides, then this becomes a classical problem. But this problem as it is called generalized eigenvector problem, and as promised, if you in MATLAB write the following command, R, B, A, this calculates you generalized eigenvalues and generalized eigenvectors immediately. So in MATLAB, there is a command for this. Now you may wonder, okay, if this is one of these, let's say this is the kth generalized eigenvector then. So because this is lambda k is there. Now, how can I combine it with this one? Final mapping. Okay. So my final mapping is it is something like this. So let me write this. This is, let me see. Okay. So this is EB step number 1, I'm writing this. First one, writing this one more time, permission. Okay. EB, step number 2, this is the second eigenvector, permission. Like similar to this one, let me write with H. Okay. Then this goes like this. This is the last one, EBN, step number 1. And I have permission over here. So I'm writing T2 one more time. And I have T1 over here. Whatever T1 is. Okay. T1 is T1. So as you see, so what is this? This is the eigenvector Fk. It's looking very similar. Let me erase this part. So my claim is as follows. So if I write an F matrix, so eigenvectors, but generalized eigenvectors, calculated by, let's say, this comment, F, then T final, which is this mapping, is also equal to, let me write this in 2 steps, is also equal to affirmation. Okay? That is it. Actually, it's not very surprising because if one of these matrices is identity, now we get our usual results like eigenvectors. In the eigenspace, I'm doing the decomposition. So how can I see this? Well, T1, if you take, for example, this one, F1 permission, F2 permission, Fn permission, so it's the permission of this matrix. So what is F1 permission? F1 permission is permission of this EB step permission times T1. EB step permission times T1. Okay. F2 permission. F2 permission is this EB step 2 second one permission times T1. So as before, now by calculating generalized eigenvectors, I can diagonalize 2 covariance matrices at the same time. So you may say that what is the purpose of this? In many problems, this is very important because you are trying to find a basis. You want to reduce the dimension of the problem. Then, in many problems, you may be happy with, let's say, in a 2-dimensional space. So you are using only, let's say, 2 of this as an example. Then, in the 2-dimensional space, how are you going to set these, space? How are you going to adjust a good space such that you have a good representation of these random vectors? This is called subspace finding. I would like to select a good subspace for my problem. And in many problems, you will end up with such an equation. Okay, we will give some examples later on. And this will be useful for that purpose. But all of this topic, you can find these in Tarian's. This is one of our textbook. Please look Tarian's textbook for almost like the same explanation, for more information, let's say. And so what we have learned? We have learned how to diagonalize covariance matrices using different methods. There can be Cholesky decomposition or LU decomposition. There can be eigenvector decomposition, and so on. If I have 2 autocorrelation matrices given like this, if I want to diagonalize both of them together, now there is also a method, this time by generalized eigenvectors, and that is it. So next time, I will post an assignment, a computer assignment, that you will conduct, and at the end of that assignment you will be doing some experiments, and you will be constructing those level curves, essentially by some Monte Carlo techniques, let's say. After that assignment, this will be especially clear, but if you cannot understand some part of this explanation, you can also read Tarian's textbook. Tarian's textbook contains almost everything, except it does not contain LU decomposition, as far as I remember, diagonalization by LU decomposition. Okay, that's all I would like to say. Okay. Now, as you see, linear algebra and classical methods such as Cholesky decomposition, eigendecomposition, etc. They are vital tools for our purposes. Okay? Because the concept of linearity and linear mappings establish a very rich structure. And using that structure, for example, such a relationship, this has been studied for maybe centuries, eigenrelation. So by making use of these classical results, we can do lots of good in many applications. Now I want to discuss, we are done with random vectors. So this is now random processes. So we are increasing, you may say, the gears. First we have started with random variable, am I right? Random variable x. We have discussed density. Now, then, we have discussed random vectors. Now we have random processes. Okay. So how do I define a random process? So again, I have this sample space. And this time it's a little different. Okay. This part is, construction of the random processes, extremely important. And you have to pay lots of attention to the details. But here is my explanation for it. Now, there is a random experiment going on. Meaning that I am picking one of these outcomes. Outcomes are the elements of the sample space. Okay? Or there is an event. This is a subset of the sample space. In any way, there is an experimental outcome, and this experimental outcome is this time initiating a function of time. Well, this is t, function of time. So, for example, it's initiating something like this. Of course, this does not start from, it can go from minus infinity to infinity. Okay? This is our representation. So the other one, let's say red one, is also initiating something like that, a function. So what's going on? So I can repeat this for many outcomes. Now we can say the following. So this blue one is, so let's say that the experiment outcome is gamma 1 of t. So blue one is this gamma 1. So let's say this is some outcome. Gamma 2. So my notation is this. This function has a, you may say, a parameter, a random parameter, gamma 2. Or it can be more complicated, but let's assume that it's like a random parameter, gamma 2. And it's affecting this time behavior of this function, because this function f includes this parameter as a function of f. So let me give an example to be more specific. This is an important example in telecommunications. Now let's say that omega, or let me write this x of t, this is random frequency, let's say cosine. X of t is cosine omega t plus, let's say theta. Okay, or let me fix this, not to confuse, plus theta 30 degrees. Okay. So what's going on? Now this is my random variable. So construction is this. From the sample space, a frequency is somehow selected. Maybe 100 Hz. Then this becomes 2 pi times 100. Am I right? So a random frequency is there. Then as soon as I have this random frequency, I see this cosine. So the parameter, the random parameter of this becomes the frequency. So random frequency cosine. So you may say that, okay, the frequency is random, but, well, I can say something about this time behavior of this function. It's always a sinusoid. No, I can say many things about sinusoids. So the main goal is studying this kind of functions. It is random, but it has a structure, as you see. It's not totally arbitrary. Okay, what is the structure of this? This cosine behavior, where the randomness is only fixed to the frequency. Of course, the phase can be random, amplitude can be random. This can be much more complicated, but in this case, only this random frequency cosine. For example, you are implementing a receiver. Maybe you are listening, you are spying over someone. So this is like frequency shift keying communication. Then you are receiving some, cosines with different frequencies. So you don't know anything about the frequencies, but you see cosines always when the frequency changes suddenly. So this becomes such an example, a random frequency cosine. So if I have something like that, how can I, analyze this? So previously, we were discussing only this omega. Then we have discussed random vectors. Maybe omega and theta can be random. Maybe the joint distributions and issue. Two random variables, you may say, or many random variables. But right now I have random processes. The issue is now it's a time function. Okay. I think we are clear with this example. Now, I want to discuss a few things. So what happens, for example, if I evaluate this, I have two functions over here at tx. So this is the end of this part. We are done with this. So I want to write a comment. These comments are very important. So number one, for a fixed random experimental outcome, this frequency you may say. So somebody is telling you the random experimental outcome that is in, let's say, gamma k over here. Not gamma, tau k over here. So this is f tau k of t is a function of time. Is a function of time. Well, if I tell you this frequency, an ordinary function of time. If I tell you that you are on this blue curve, and this blue curve is just a function of time. Okay. Very good. Now, if t is random, so this is called a process variable. This can be time, space, anything actually. It's just a process variable. For this course, in general, it will be t, time. If t is fixed to, let's say, a specific time, tx. Okay? So what do I have? So forget that this is extending from minus infinity to infinity, this t. Now I'm only observing, maybe my lifespan is thus just this tx. I am not worried about what's going on before or after. Okay. Now, I have then such a case, f1 tx, f gamma 2 tx, and so on. So, in other words, at this tx time, maybe you observe this value, okay? Because this function is passing through this value at tx. Or the red one, this is the other experimental outcome. So you are either observing this or that. So, sorry, let's say that in the sample space I have only these two outcomes, maybe coin toss, okay? Heads and tails. So blue is heads, let's say. If it is heads, then you observe at tx this value. Then if red is tails, then you observe at tx this value. Okay. So what's happening? If they are equally likely, this head and tail events. So these are actually random variables, then z is equal to f tx. Okay. This let me write. Well, okay, let's write. Okay, f tx. I don't want to use. Okay, f. So this becomes a random. So what do you see about this? This becomes a random variable. Z becomes a random variable. Okay? Because as you see, right now there is no t dependence. You are evaluating this random process at a specific time. Okay? Well, that is interesting. So, each one of these functions, red and blue functions, they are called a realization. A realization of random process. A realization. Realization means like a bird, okay? So something happens and you have this red function. This is a realization of this random process. Another realization of this random process is the blue function, and so on, okay? So each one of these are realizations for a fixed random experiment and for a fixed outcome, random experiment outcome. Now, if you don't know anything about random experiment outcomes, if you fix the time index, then you have a random variable. So, any guesses? If I fix two random times, we get random vectors this time. Okay? If I have, let me write it, because it's something easy. Let me write 3. If z is equal to, z1 is equal to f of tx, z2 is equal to, let me write t1 because it will be more natural, f at time t2. Okay. And f is like random process. So tilde, this is our earlier notation. This represents, sometimes I use this. This denotes a random process. Sometimes I may use this, it's useful, but this is an older notation from Papyrus. Okay. We were using Papyrus textbooks for a very long time, and it's very valuable, but it's actually better on board because we can put tildes, capital and small letters because of this matrix issues. There can be confusion, but tilde may be a better notation, but we are not using it anymore to be compatible with the current textbooks. Okay, in any way, then this would be a random vector. If you fix, okay, if you fix two time instances. Now I have this green time instance, and let me have another green time instance. Let me call this ty. Okay. So let me mark this with some shading. Okay. Now, coin toss. If it is heads, you see this and that. If it is tails, you see this and maybe 0. Okay. That is it. So there is a joint distribution as you see. Okay. For example, this is high value and 0 if it is tails, because it is, red. Okay? So this vector, high value and 0, it is tails. You can understand something about this. And you can say, can you predict, if you know tx value, can you predict ty value? Well, if this is high value, meaning that I have two possibilities, this height and this height at tx. So if you know these possibilities, and you observe that at tx you get this high value, so you don't need to even look at this, because you know that red value will be passing through 0. So you can do some, you may say, predictions. Okay. So this will be the thing that we will be discussing. This will be the nature of random processes. So by analyzing this random process at a given time, I can maybe say something what's going on, what has happened before, after. What will be, so this will be our discussion. Okay. So I'll be making use of such observations later on. So random processes, that is the reason it is a very critical tool for our purposes, because in real life, when you are doing experiments and so on, you collect data, and that data, you cannot explain it with deterministic methods, like in this random frequency cosine. You are listening to a communication system, you just see random events going on. So what can you say? There is some structure over here, but how can I define this structure? And how can I make use of this structure? That will be our topic. Okay? So it's not arbitrarily random, there is some structure, and how to make use of that structure is the goal of random process discussions. Okay, now I would like to discuss, but after a mini break, I would like to discuss descriptions of random processes. Okay. So we will continue immediately after the break.